we are discussing the thermal history of the universe, and in the last class we have seen that as the universe expands, the momentum of a free particle scales proportional to 1 by a, the scale factor. So, as the universe expands, the momentum of a free particle falls as 1 by the scale factor. It keeps on decreasing. We also saw that the occupation number of any state with a certain value of the momentum is given by one by exponential epsilon minus mu by kBt, where epsilon is the energy corresponding to this momentum, mu is the chemical potential, kb is the Boltzmann constant, and T is the absolute temperature. So, this is if I have a system in thermal equilibrium, set of particles in thermal equilibrium, the occupation number of any state with a particular value of the momentum is given by this expression, and plus is for Fermi particles and minus is for Bose particles. And the energy of the particle in general is m square c4 plus p square c square the whole to the power of half. Now, we had also seen that if we take the limit where kBt, so the temperature is such that it is much higher than the rest mass of the particle, then we may ignore the rest mass contribution, which is this term in the expression for the energy, and the occupation number then can be written as so this is when kBt is much greater than the rest mass. The other extreme, which is also of interest, is when the temperature is such that kBt is much smaller than the rest mass of the particles. In this case, this expression for the energy of the particle, it is convenient to approximate this as m c square. We can write this as m c square into 1 plus p square by m square c square to the power half, which is approximately equal to, so we do a Taylor series in this, this is assuming that it is a small number, and this is approximately equal to mc square, and then I have the first term, which is going to be half p square, 1 m will cancel out, 1 c, this will be m square c p square c square, and the c will cancel out. So, we have p square by 2m, and there will be higher order terms which we can neglect in this limit. So, in this case the occupation number can be written as exponential m c square minus mu plus p square by 2m, the whole thing, by kBt plus minus 1. Now, this mc square is also a constant, so we can absorb it inside the, redefine the chemical, or we can, okay, for the time being let us leave it like this. Now, in this case typically the exponential term is much larger than 1, and we can ignore this plus minus 1. So, this becomes approximately equal to so in the limit where the temperature is much smaller than the rest mass, we can approximate the occupation number in this form. Now, this is the Maxwell-Boltzmann distribution, and this, the overall number out here does not depend on P. So, we can treat it at a given temperature, we can treat this as a constant. So, we can write this as A, this is equal to A exponential minus P square by 2m kBt. So, we have seen the two different limits. The first limit is when the temperature of the system is much higher than the rest mass energy. The occupation number is given by this, where the rest mass energy does not figure in the expression for the energy of the particle. The other extreme is when the temperature is much smaller than the rest mass energy, and we can approximate the occupation number by a constant into exponential minus p square by 2m kb into T. This is the Maxwell-Boltzmann distribution. Now, the question is what happens as the universe expands. So, let me remind you of what the problem that we were discussing is. So, at the time T I, the system is in thermal equilibrium with a temperature T I and say a chemical potential mu I, and we would like to find out what happens to the system at a later, what is the occupation number at a later time Tf, what does the distribution of the particles in the different states look like at a later time Tf. So, we would like to calculate Nf, the final distribution, as a function of P at a time, at a final time, and we have seen that we can write this as the initial distribution for a different value of the momentum. For a value of the momentum A, this is the scale factor at the initial time, this is the scale factor at the later time when we want to calculate the occupation numbers, the particle distribution. So, if I want to calculate the particle distribution for a momentum p, the final particle distribution, this is equal to the initial particle distribution for a momentum p into the final scale factor divided by the initial scale factor. And for the relativistic situation, so the relativistic situation refers to this. So, here the final distribution function, the final distribution of occupation numbers can be written like this. So, we have written the final occupation numbers or the final distribution function in terms of the initial distribution function, but the value of momentum is now different. It is A, the final scale factor, divided by the initial ratio of the scale factors into the momentum. Now, this ratio of the scale factors here multiplies the momentum. We can get rid of this by just putting in a scale factor dependence for both the chemical potential and the temperature. So, what we can say is that the final temperature is the final chemical potential again is the ratio of the scale factors, the inverse of what the momentum change is like. So, if we define this, then we can say that the final distribution function, the final occupation number is given by 1 by exponential P c minus mu final by K b T final plus minus 1. So, what we have seen is that as the universe expands, this expansion of the universe can be accounted for relativistic particles by saying that the form of the occupation number of the particle distribution in different momentum states remains unchanged, except that the temperature and the chemical potential both scale inversely as the expansion of the universe. So, as the universe expands, the chemical potential falls as 1 by the scale factor, the temperature of the distribution also falls as 1 by the scale factor. This is for relativistic particles. Let us now see the same thing, and we had for the non-relativistic situation. So, for the non-relativistic situation, the final distribution function is the initial distribution function at a different value of the momentum. The different value of the momentum is AF by AI into this P. So, this will be squared divided by 2m kb T initial. So, this is the final distribution function or the final occupation numbers. It is related to the initial function, just that you have to replace P by the value of the momentum at that epoch, which is the ratio of the scale factors AF by AI into P. And since the occupation depends on the square of the momentum, the square of that comes over here. Now, we can write this again as A exponential minus p square by 2m kb Tf, where the final temperature is equal to, now you see that the final temperature, if you want to relate it to the initial temperature, it will be Ai, the initial scale factor, divided by the final scale factor square. So, what we see here is that the relativistic particles and the non-relativistic particles, let us say that they are in thermal equilibrium at the same temperature, and then somehow, and then with the expansion of the universe, the temperature of these two species behaves in different ways. So, for the relativistic particle, let me summarize what we have learned here. For the relativistic particles, the temperature scales as 1 by the expansion, the scale factor. For non-relativistic particles, the temperature scales as 1 by the square of the scale factor. So, for non-relativistic particles, the temperature falls much faster with the expansion of the universe as compared to relativistic particles. Now, let me just remind you of a few more things. Okay. Now, the chemical potential here for non-relativistic particles has gone into this constant A, and the value of the chemical potential through this constant A does not change with the expansion of the universe. The number of particles remains here, remains fixed, it does not change. Now, there are, so this is the behavior of relativistic and non-relativistic particles. So, let me give you examples. For example, if I have neutrinos, so neutrinos, if they have a mass m, which is much smaller than the temperature kBT divided by c square, they behave like relativistic particles, and as the universe expands, the temperature of this neutrino background of these neutrinos, which were at thermal equilibrium, let us say at some time, and then the universe expands where they move freely, the temperatures of that distribution will scale as 1 by the scale factor. An example of non-relativistic particles, let us take hydrogen atoms. And temperatures say of few thousand Kelvin, these can be very well treated, the hydrogen atoms, as non-relativistic particles, and as the universe expands, if I have hydrogen atoms which are in thermal equilibrium at some time, and then they are not, they evolve freely after that, as the universe expands, the temperature of these hydrogen atoms will fall as 1 by a square as the universe expands. These are non-relativistic particles at temperatures of few thousand Kelvin. So, these are two examples of relativistic and non-relativistic particles. Let me also tell you about a little bit about neutrinos. Suppose we have a neutrino species, a cosmological neutrino species, whose mass at present is greater than kB T by c square, where this T is the present temperature of the photon or the neutrino background. So, T is of the order of 3 Kelvin, and the mass of the neutrino is, let us say, much more than that. And let us also assume that these neutrinos, they were in thermal equilibrium with the CMBR and the rest of the universe at some temperature which is much higher than, so when they were in equilibrium, the mass was much lower than Kb, and then they go out of equilibrium at this temperature, they decouple and they move freely after that. So, when they decouple from the rest of the universe, when they go out of thermal equilibrium, the neutrinos have a distribution occupation numbers which is given by this with a plus sign, they are fermions. Now, as the universe expands, the occupation number of these neutrinos of a particular state is unchanged, only the momentum corresponding to that state falls as 1 by the scale factor. So, as the universe expands, the occupation number of that particular, of any particular state is unchanged. So, even at present, even though the mass of the neutrino is much more than the temperature of the universe at present, I would still have to use this formula to calculate the occupation number of these neutrinos. So, I would have to, given the present momentum of the neutrino, I would have to go back to the epoch when they were in thermal equilibrium and calculate the momentum, and then use this this occupation number, this distribution, to calculate the occupation number at present. So, one has to be careful and in how to treat a particular species, as whether it is relativistic and non-relativistic, and whether so which of these to treat it as. So, this is just a word of caution. Now, so we have seen how the temperature, how the occupation number, the temperature, chemical potential, all of these things change as the universe expands. Now, next let me discuss another interesting quantity. This is the specific intensity. Okay. Specific intensity. So, before discussing the specific intensity, there are a few background things which I should tell you. So, let us go back and consider a volume of the universe, a volume L of side L. So, the volume is L cube, and the modes that this volume can support, they are labeled by, they have k vector. So, there will be different modes which this volume can support, and these modes will be are given by, so the modes will be k is equal to 2 pi by L into nx, ny and z. These are integers, nx, ny and z, and each set of integers labels tells you one wave vector k, and corresponding to every wave vector k there is a momentum p, which is h cross k, and we have just seen the occupation number of a state of a certain, of any given mode with a certain value of p, which is given by the expression we were just discussing. So, now let us ask the question, how many particles are there per unit volume? So, let us call this dn, the number of particles per unit volume with modes, with number of particles per unit volume with in a certain momentum range or in a certain range of d cube k. So, this is given by d cube k can be written as k square dk into d omega in spherical, where d omega is the solid angle. So, in spherical polar coordinate system, d cube k can be written like this. Now, the number of modes corresponding to d cube k, if I want to convert this to the number of modes, then this is going to be this into L cube by 2 pi cube. This is the number of modes, and then we are interested in the number of particles per unit volume. So, this is going to be Np, where P is the occupation number of a particular mode, where you can calculate, given K you could calculate P, and this is going to be divided by L cube. And then for photons, for example, we have these are spin 2 particles. So, for photons we have a factor of 2 over here. For neutrinos also there will be a factor of 2. So, for irrespective of whether they are photons or neutrinos or electrons, there will be a factor of 2 coming over here. This is a degeneracy. So, this gives me the number of particles per unit volume with p values or k values in this range. Okay. Now, this can also be written as 2, and then we can put in the expression for the occupation number. The occupation number is, let us assume that the particles are massless. If the particles are massless, then the dispersion relation is that k is equal to omega c, and the energy we know then is h cross omega. So, we can write this as exponential h cross omega minus mu. Let us also assume that the chemical potential is 0. So, by kb T, if required we can put in the chemical potential minus mu plus minus 1. So, this is the occupation number, this is a factor of 2, the L cube cancels out, there is a factor of 2 pi cube over here, k square k d omega. Now, there should be a this is correct. So, this cancels out, and then we have a factor of 2 pi cube over here. And k is equal to omega c. So, other way around, omega by k is equal to c. So, this can be written as omega square d omega into d solid angle divided by, so k is equal to omega by c divided by c cube. So, this gives us the number of particles with omega in the range omega and omega plus d omega traveling in with angular frequency in this range, and traveling with in the solid angle d capital omega. Now, let us now, so given this, let us now calculate the specific intensity which we shall define now. So, specific intensity is defined as follows. Let us take a unit surface of area dA and ask the question, what is the energy that comes in through a solid angle d omega. So, given an area dA, a solid angle d omega, how much energy comes in the frequency interval d nu in the time interval dt? Let us ask this question, and this is given by the specific intensity into all of these quantities. So, the specific intensity essentially tells us the energy coming in per unit area, per unit solid angle, per unit frequency in unit time. This is the definition of the specific intensity. This is defined for radiation, so for photons. Which are Bose particles. So, let us assume now that we have what we call radiation in thermal equilibrium. This is called black body radiation at a temperature T. So, we have black body radiation in thermal equilibrium at a temperature T, and we know that the occupation number for this radiation, let us calculate the specific intensity for such a radiation. So, we know that the number of photons per unit volume dN is given by 2 by exponential h nu by kBt minus 1 into nu square d nu d solid angle divided by, so I am writing the same expression except that I am writing it in terms of the frequency. The factor of 2 pi cube is gone once I write it in terms of frequency, and we have a factor of c cube over here. And we can convert this to the energy per unit volume. So, the energy per unit volume is, this is the energy per unit volume, that is the number of photons per unit volume with frequency in the range nu and nu plus d nu. So, this is the energy per unit volume with frequency in the photon with frequency in the range nu plus d nu. So, if these are photons, let us ask the question, what volume, the entire volume C dt into dA, all the photons in this volume travelling in a solid angle d omega will cross through this surface in a time dt. So, we can say that dE is going to be this quantity h 2h nu cube by c cube exponential h nu by kBt minus 1 . So, this is the energy that will cut across the area dA in the time dt in the frequency interval d nu per travelling, the photons travelling in the solid angle d omega. So, from this we can straightforward identify what the specific intensity of black body radiation is, and we see that this is given by 2h nu cube by c square, 2h nu cube by c square, and then we have 1 by exponential h nu by kBt minus 1. So, this is the specific intensity of black body radiation, and there is a very useful form in the limit where h nu by kb t is much less than 1. So, in the limit where this is much less than 1, we can do a Taylor series expansion, the one factor cancels out, and we have kBt in the numerator, h nu in the denominator, one factor of h nu cancels out. So, the specific intensity then becomes 2 nu square by c square kBt, which can also be written as 2 kBt by lambda square. This is the Rayleigh Jeans limit of the black body, specific intensity of black body radiation. Another, so this is very useful in discussing the properties of radiation. Another quantity of interest is the total energy density in this radiation. So, how will we calculate the total energy density? So, that can be calculated. To calculate this, let us go back to the formula for the number density of photons. Right, we can, for any particle species, this can be calculated as follows. So, we have to multiply this with h cross omega and then do the integral. So, the energy density U, this is given here. We can straight away do the solid angle integral when calculating energy density, because we are now interested in particles traveling in all directions. So, we can integrate over d omega, and this gives us a factor of 4 pi. 4 pi into 2 gives us 8 pi. So, we have 8 pi, and then we have 2 pi cube c cube, which can also be taken outside, two pi cube c cube has gone out, this factor of 8 pi has gone out, and the integral that we are left with is omega square d omega divided by exponential h cross omega by kBt plus minus 1, depending on whether they are fermions or bosons for relativistic particles. Here we can define a new variable y, which is h cross omega by kBt, whereby this integral becomes y cube, y square, sorry, there will be a factor of h cross omega, because we are calculating the energy density per unit volume. So, there will be a factor of h cross omega here, another factor. So, this will be y cube dy divided by and let us get the factors correct outside. So, we have 8 pi, here also we have 8 pi cube. So, we have 1 by pi square c cube, and we have to put kBt to the power of by h cross to the power of 4 to compensate for making this y, and we already had a h cross. So, we have to divide this by 1 by h cross. So, this is something which is there, and we have to evaluate this integral. So, the important thing over here is that this depends only on the temperature. The rest of these things are constants. This integral is a constant, h cross kb c, these are all constants. So, finally, finally we can write this as the internal energy. So, for photons we are interested in photons. So, for photons this is restricted to -1. For the time being, let us focus our attention on thermal radiation. So, -1, and for photons at a temperature T, the internal energy is given by the internal energy is given by this into T to the power 4, where the quantity in the brackets over here is called the Stefan-Boltzmann constant AB. Stefan it is the Stefan-Boltzmann constant AB. So, the internal energy can be written as AB T to the power 4, and the Stefan-Boltzmann constant has a value (10 to the power minus 16), 7.56 into 10 to the power minus 16 joules per meter cube per Kelvin to the power 4. So, this gives us the energy density in black body radiation, in thermal equilibrium with matter at a temperature T, and it has a dependence T to the power 4. So, that is why this constant has a Kelvin to the power 4 over here, and if you multiply it with T to the power 4, this gives us the energy density in joules per meter cube. Now, it is also convenient in cosmology to express it in this form. So, it is also convenient to express it in this form, where when you multiply the Stefan-Boltzmann constant with T to the power 4, T being in Kelvin, you get the energy density in kg per meter cube. So, you have to just put in appropriate factors of c square to convert joules per meter cube to kg per meter cube. Kg per meter cube into c square will give us this, right. So, it is also convenient to sometimes express it like this. So, now we have learnt in cosmology that the whole universe at present is filled with a radiation whose temperature is 2.7 Kelvin. So, given this radiation background, this thermal black body radiation at 2.73 Kelvin, we can use this thing that we have just derived, that the energy density of this radiation is AB, the Stefan-Boltzmann constant, into T to the power 4. We can use this to estimate the density in this radiation. So, the energy density in this radiation this can be calculated by just multiplying the AB T to the power 4. Now, we compare this with the critical density of the universe, which has a value So, the energy density in the radiation you can see here is going to be of the order of, if I multiply it with 3 to the power 4, 3 to the power 4 is of the order of 100. So, it is going to be of the order of 10 to the power minus 31 kg per meter cube. And the critical density of the universe at present, so this is going to be of the order of 10 to the power minus 31 8 into 10 to the power minus 31 kg per meter cube, and the critical density of the universe has a present value of 1.88 10 to the power minus 26 h square kg per meter cube. So, the ratio of these two gives us the density parameter in this radiation in photons present. This is the density parameter of the CMBR, contribution to the density parameter from the CMBR, and this turns out to be 2.5 into 10 to the power minus 5 h minus 2. So, at present this makes a very minute contribution to the total density of the universe. It is roughly 1 part in 100,000, 10 to the power minus 5. Maybe a little more than that, because we have this factor of h minus 2 and h is less than 1. So, this will be somewhere between 10 to the power minus 5 and 10 to the power minus 4. So, this radiation which fills our universe, the cosmic microwave background radiation, at present makes a very small contribution to the dynamics of our whole universe. The contribution to the dynamics is essentially quantified by the density parameter. So, it makes a very minuscule contribution to the density parameter. That is what we see. Now, we also know though that the energy density in these photons, this scales as T to the power 4, and the temperature we have seen scales inversely with the scale factor. So, this is going to be the Boltzmann constant, the present value of the photon into a to the power minus 4. So, as you go into the past, as the universe gets smaller and smaller, the energy density in this radiation component, the cosmic microwave background radiation, scales as a, the scale factor, to the power minus 4, or you can write this as 1 plus z to the power 4. It scales up with redshift as follows. We have also seen that the matter content of the universe So, this is how it scales with redshift. The matter content of the universe we have seen scales as the present matter density into a to the power minus 3, or this scales proportional to 1 plus z cube. Now, at present the matter density, so at present this has a value, so at present this number has a value of the order of 10 to the power minus 5, 2 into 10 to the power minus 5 into h to the power minus 2. This value has a value of the order of unity, somewhere around 0.3. This is at present, but if you go into the past, as you go into the past, this will scale as 1 plus z to the power 4, this will scale as a smaller power of z, 1 plus z to the power 3. So, at sufficiently high redshifts, this term will overtake this, and we shall go into the radiation dominated era. So, we can easily find out when these two will become equal. So, this is called the epoch of matter radiation equality. We would like these two terms to be equal. This is called the epoch of matter radiation equality, and multiplying both of these with a to the power 4, what we see is that A equality is given by the ratio of the energy density of the CMBR divided by the matter density of the universe now. So, this comes out to be somewhere around between 10 to the power minus 4 and minus 5. So, around a redshift of 10,000, the universe, which is now matter dominated, goes into a radiation dominated era. Now, this matter, so before a redshift of around 10,000, the universe was dominated by radiation, and that is the radiation dominated era. In this calculation, we have just considered the energy density of the CMBR. We shall learn later that the neutrinos also make a contribution to the relativistic particles, and that also will affect the matter radiation equality era. It will push it a little earlier. So, taking all of these into account, we find that around a redshift of 10,000, we had a transition from the current matter dominated era universe to the radiation dominated universe at high redshifts. So, today let us stop here, and tomorrow we shall resume from the same place.